We've been looking at some AEC particle data from the Lee particle detector to try to see if we can distinguish two mechanisms of solar wind particle injection at the cusp. Here I've illustrated the first injection mechanism that we've tried to look at, and that is through magnetic merging at the nose of the magnetopause. You have a pointer? And what I'm trying to illustrate here is that if merging occurs, if injection occurs through merging at the nose, one expects a velocity dispersion of cusp particles because you're combining a parallel velocity, which brings the particles from the injection point down to the satellite at low altitudes, with an E over B convection velocity towards the pole. This velocity is the same for all the particles, and this velocity depends on the energy, so that as a result of this, one expects the highest energy particles to appear first down at low altitudes, and the progressively lower energy particles to appear at progressively higher latitudes. The next slide shows the other injection mechanism that we've looked at, namely particle diffusion across field lines in the cusp. Now, I should point out that the stationary particle trajectory kind of injection that Keith talked about generally brings particles across the magnetopause only by a few gyro radii, at least on the day side. And the observations of the latitudinal width of the cusp show that the injection mechanism somehow has to transport particles very efficiently across the field lines. The latitudinal width of the cusp is several thousand or tens of thousands of gyro radii at the least. So diffusion would be the other possible way that we've looked at of getting particles across field lines and spreading the cusp in latitude. And tried to illustrate here that if the diffusion random walk step size is proportional to the particle gyro radius, then one expects that a diffusive injection should result in an opposite kind of velocity dispersion. Here, if you look on the poleward side of the cusp, you should see the highest energy particles penetrating most deeply onto the poleward side of the cusp, the open field line region. Pat's now going to talk about some observations that relate to the distinction between these two mechanisms.
This shows the merging type dispersion that was his first case. The highest energy protons arrive first, followed by the lower energy protons. The model gives a specific 1 over lambda squared. This fits this 1 over lambda squared to an excellent degree. I have a slide which he won't let me show that resolves what the source spectrum was that produced the velocity dispersion, and it's very exciting because it shows that these are not, the source is not pure proton magnetosheath spectrum, but an accelerated proton magnetosheath spectrum. Last slide. This is what we've taken the fact that the fastest ones arrive first and the slowest ones arrive next, and we've deconvolved the original source spectrum for the protons that we saw in the cusp. And interestingly enough, this is not magnetosheath. If you say that's magnetosheath velocity, your temperature is way too high. In other words, we suspect that this is stagnated flow that had a big temperature that's been merging, has given it an alpha velocity, field line velocity that's come down. When we fit it to the lambda, 1 over lambda squared, to find out the dispersion, we have onboard convection velocity measurements. Rod Helis gave us the measurements. We were able to find the field line distance to the injection point. It turned out to be very close to 20 RE. So it's all very self-consistent that this is coming in from the nose. It's more energetic than magnetosheath stuff is at the nose. Tanis, you come?
Yes, I'm always puzzled when someone speaks of the magnetosheath spectrum.
That's true.
In fact, the magnetosheath temperature can vary from essentially equal to solar wind velocity down to the solar wind temperature.
That's true.
And so I can only speak of magnetosheath spectrum at a specified location.
That's right.
Then I have to say how one gets it, from the Spider's models or from what. And what I use in your case when you say it's not a magnetosheath.
Okay. Well, if you look at Spider's model, if you look at Rosenbauer's polar magnetosheath data, you either get flow velocities of a couple hundred to 300 to 400 kilometers per second, say at the polar cusp, but a temperature of only like 100 eV. And you look at proton data, and a temperature of 100 eV at a flow velocity of 300 or 400 kilometers per second is about what is typical at the polar cusp for the proton data.
Yes, but the velocity expected to be proportional to solar wind velocity.
That's true.
Not variable a factor of
That's
2
true.
from time to time.
That's true. That's true.
So
But
basically you're comparing the Mach number then.
I have never seen, and I've looked at many months of solar magnetosheath data, I've never seen a temperature that high and a flow velocity that high in the magnetosheath anywhere.
So you also understand the flow velocity can be almost anything depending what it's doing in the solar wind. So the only thing one has to look for is the Mach number. And on the Mach number in the magnetosheath varies from 0 at the nose and down to solar wind value far downstream.
That's true.
So you can always find a place in the magnetosheath which would correspond to the Mach number you're seeing here. The only question is, where is that place? Is it at the nose, or is it at 10 degrees away, or 30 degrees away, or what? That's the only question you can really pose in this case.
Mach number here is of the order of 2. I think it's between 2 and 2.5. And you can't find that kind of Mach number in the magnetosheath according to the usual flow calculations unless you go considerably behind the cusp. The Mach number near the cusp is more like between 1 and 1.5. So we're looking at plasma that had to come in the usual flow model either from behind the cusp, which is very hard to understand how it got turned around and came back towards the Earth, or else plasma from near the nose that has been accelerated through some process other than the usual expansion of the flow. And this is the point that we're making.